All right, everyone, welcome back. We're going to jump into the Shadish Cook and Campbell material right away here. We're going to cover a couple of chapters in one set of slides. So we're going to cover the validity chapters. Now, as I go through this, I'm going to be repeating a lot of what's in the book and then adding my own stuff here and there. So in reality, there's a lot of slides here, but I'm not going to be talking about everything in gross detail. Definitely, probably not as much as what I did on the last topic, because with regard to the threats to validity, your book does an extraordinary job of covering the material. And these Cook and Campbell in 1979, they really laid this stuff out, and it really hasn't changed. It's just they're kind of the leaders in the field. They really identified all these threats to validity, and in terms of having it presented to you, there's not much of an easier way to present it than what Cook and Campbell did. I'll boil down a couple of things for you that I think might be a little bit confusing, and just kind of give you a summary of the entire chapters. So we'll go through and cover this stuff right now. So hope you enjoy. Here we go. All right, let's go ahead and look at validity. Now, we've already defined it in general, and I've talked a little bit about internal validity, talked a little bit about external validity. So in a sense, this is already done, but I do want to kind of expand on what the authors are talking about a little bit. And they're talking about the truth of an inference, right? So remember, the theme of this textbook and the theme of this class is partially understanding what what a scientific fact is, and how does that relate to a concept called truth, right? Truth is something that is an odd sort of thing, right? Truth is, in a sense, a personal sort of thing. It's something that you decide whether or not something's true based on the evidence that has been presented to you. Now, truth in science is very strict, right? We have a lot of rules with regard to that, and that's what we've been talking about so far with causal inference and those types of things. But it's different. It's a personal decision when it's outside of science, and so it makes it a little bit wishy-washy. But anyway, that's a total tangent that I tend to get off on. So here we go. The truth of an inference. So what we're talking about, the truth, so the accuracy of the conclusion, right? The inference, you do a study and you draw a conclusion based on that. That conclusion is the inference. That's what we're talking about. So quite simply, validity is referring to the truth of one of those inferences, right? In other words, is it true and capable of being supported by the evidence? So the evidence that you gathered from your study, you're going to draw conclusions from that. Those conclusions will become an inference. You're going to make an inference about your data, right? And then the question becomes, is it true and capable of being supported, right? Based on what you did? So there's all sorts of different types of validity, as you might think of, right? And you also may think about the fact that it's never really 100%, right? You can never have a 100% valid study, right? It just can't be that way. And we've already talked a little bit about that in terms of, if you try to maximize one type of validity, you tend to weaken another type, right? And even if you do the world's best study, the one that's never been performed yet and probably never will be, right? You'll still not have 100% validity, because there'll always be questions about your measurement tool, your sampling method, or whatever the case may be. Validity is really a property of inference, not a design in itself. Now, this is a bit odd to think about, because from here on out, we're going to talk about it as being solved by design. So we do need to make that distinction, that a particular design, whether that be a quasi-experimental design or a randomized experimental design or a case study design, those particular designs do not fall into the category of valid or not. You don't describe things that way. The design itself is just the design. That's how you're going to get your evidence, right? And that evidence, okay, will be able to support certain conclusions, right? So the question is that, the comment then is about validity being related to this property of an inference, right? So, and not the design itself. Although different designs affect validity. Validity is not something that's applied to one particular design type. Some designs, however, tend to produce more valid evidence than do other designs. In other words, they tend to produce more quality inferences than other designs do. But again, it's not a property of the design. It's a property of the inference, the results that come out of the design. It's a fine distinction, but it's an important one, because you don't want to get wrapped up in the thinking that, just because I did this really good design means I have the world's best data or the most valid data. That's not the case. You could do a really awesome design and have really crappy data. So anyway, let's move on. All right, 4 types of validity as identified by your authors. There's actually, every research, every specialist in research methods and if they write a textbook, they tend to add their own, right? Shadish, Cook, and Campbell really broke these down into these particular 4 types of validity. But theoretically, you could break them down a little further. They added some that historically weren't there. It used to be just internal, external, right? And then Shadish, Cook and Campbell in '79 added the statistical conclusion and the construct validity. Sometimes people talk about construct validity as a type of external validity. I've seen authors talk about ecological validity, which is just a special case of external validity. So there's all sorts of different types of validity here. But internal validity is the one that I tend to focus most heavily on in terms of thinking it's the most important, but that's my bias, all right? Other people are going to say external validity is the most important. So internal validity, did your design allow you to detect the effect if one is there, right? So did the independent variable have an effect on the dependent variable? If it did, can you detect it? Right? That's what we're talking about with internal validity. So depending on how you design your study, you may be able to detect that effect or not. Right? So again, there's where it starts to get confusing. Notice I'm talking about how you designed it then relates to validity. Okay? But validity is how you interpret the results, right? The evidence. It's not the particular design. Some designs, again, will produce more internal validity, will be higher in internal validity than others, but that doesn't mean that the results that come out of that are still meet the criteria for causal inference. All right. So internal validity, ability of your experiment to detect an effect. Did that IV affect the DV? Right. External validity. Who do these results apply to? This is often thought of as generalizability, and it's a little bit bigger than just that, but that's the easiest way to think about it. So you've got your study, you've got your 100 people, 400 people, 1,000 people, 10,000 people, 4 people, 2 people, 1 person, whatever it may be. Who do those results apply to? That's going to be the question that is addressed with external validity. Statistical conclusion validity, and there's a couple of things here, where the correct statistics used on the data, that tends to be, there's a little bit that I'm adding a little bit there, right? That's kind of an interpretation from what your authors are talking about, right? But what your authors really said was, can we make a reasonably accurate inference based on the data that we have and based on the procedures that we're using and based on the statistics that we're using? Right? So if I use a correlation, if I use a Pearson product moment correlation, which is just a simple correlation, I'm not going to be able to make certain inferences from that. Right? But maybe if I used a t-test, I could make some more inferences. So I tend to put the correct statistics under the statistical conclusion validity because it's important. And one of the things that I'm going to try and hammer home this quarter is about making sure you understand when the correct statistic has been used, because quite often, and it's extremely prevalent in our field, that we don't use the correct statistics. It seems unheard of. It's like, what do you mean they don't use the correct statistics? They're using statistics, right? But there's specific stats apply in specific scenarios. And a lot of people are not well versed in those things. And you'll see a ton of research, and you'll look into the school psych research. And if you're familiar with statistics, if you're familiar with research design, you'll realize that sometimes, and more often than we care to admit, that the authors that are getting published actually didn't use the correct stat for that data. Now it's getting better because there's people like me all over the world that are getting annoyed at the fact that our field is being filled up with incorrect stats. And the problem with doing incorrect stats on your data is that you then can't draw any reasonable conclusions from it. Right? So your stat will work, the numbers will work, the formula will be filled in with the numbers, and you'll get a result, but it doesn't mean anything. But if you don't know that it doesn't mean anything, then you'll move on and pretend that it does, and you'll obfuscate and confuse the science and the field. But as I've said before, science is self-corrective, so it will fix itself. But it's still a pet peeve of mine, and it drives me insane. In fact, we'll talk about it. Your Rubin text also talks about it a little bit, and we'll get into that as well later on in the quarter. And the last one, construct validity. Do these inferences accurately represent a construct? According to your authors, constructs are what we're really studying in psychology and the social sciences. We're studying these things called constructs, and we relate constructs to each other in order to understand the world. So you might ask, what the heck is a construct? Well, a construct is just something that you make up, all right? It can be hypothetical, it can be empirical, it can be all sorts of things, but a construct is just something that's created, it's constructed, right? So intelligence is a construct. Let's see what else. Development is a construct. There's all sorts of things that are constructs. Personality is a construct. All those things are constructs. So the question becomes, did we measure that construct accurately? So if I'm doing an intelligence test, what happens if I give you the Army B? And go ahead and pause and look up what the Army B is. You might be able to find it on Google Images. But the question is that Army B, the letter B, is that intelligence test a valid test? In other words, does it have construct validity? Okay? And how valid is it in terms of measuring the construct of intelligence? So we've got all sorts of problems with regard to construct validity, and in my experience, it's one of the most overlooked areas. But that's partially because I'm not in an area where I tend to look at constructs that much. The research I do tends to look at behavior and behavior alone. I tend not to do survey instruments and things like that. I tend to be very behaviorally oriented and tend to focus on how many times did the child hit the other child, or how many math problems did the kid get correct, and things like that. And I tend to shy away from a lot of the intelligence testing and the construct assessment, just because of the problems that are associated with construct validity. So part of the reason that I see it downplayed is, at least in the work that I do, is because I don't do anything with it, right? So I'm sure people that do more testing and assessment in a different way see it as much more prevalent in their life. So I might be leveling an unfair complaint against the field by saying it's the most overlooked one. So I don't know, but at least I'm being honest with my biases here. All right, let's keep going. All right, let's look at threats to validity. Now, these are the things that are evil, right? These are things, reasons, situations, procedures, events, whatever. They're anything that can happen that can damage our ability to make accurate inferences. These are the enemy, right? So we seek to remove them. Our goal as an experimentalist, or as any experimentalist, when they design a study, their goal is to reduce the threats to validity, to remove them if at all possible, to minimize them, to hide them, to make them, to nullify the threat. Okay? And quality design is really about having a preemptive strike on your threats to validity, right? We can put it in all sorts of terms of war because it's kind of funny to do that, but you get the idea, right? In reality, what threats to validity are confounds. Right? You've heard about confounds. We've talked about, I'm sure you've talked about them in the past in other courses, and you've heard me talk about them already in this course. But confounds are really, more specifically, they're thought of as threats to validity. In other words, it's confounding your ability to make accurate inferences, to draw conclusions. This is where the criticisms of studies exist. Okay? When you criticize a study, you don't say, I don't like that study because I don't like their results. That's not a valid scientific criticism. I don't care if you don't like the results or not. The results are the results. But you can criticize the study based on the threats to validity that are present in the study. Right? So did you control for everything you possibly could have? Did you not randomly assign? Did you not randomly select? Was there a history effect? Was there a maturation effect? We'll talk about all those things. Right? But the point is that when you evaluate and critically analyze research articles, you do it along the lines of threats to validity. So when we get into these threats, there's threats for each type of validity: internal, external, statistical, conclusion, and construct validity. There's a list of threats for each of those. Essentially what you want to do is take those threats and understand them, learn them, and become very familiar with them, because when you read any journal article, you need to have all those threats to validity present in your head. You need to be thinking about all those things. In fact, in grad school, we had an assignment to list all the possible threats to validity, define them, and then come up with a method for controlling for them. And I got tired of hearing about people complaining about this assignment, so I pissed off my professor, and I made a gigantic poster. It was like 5 feet long, and I listed out all these threats to validity and how to control for them. And I'm assuming that probably to this day, you can go down to WSU and find a poster where all of these threats and how to control them are posted on a wall somewhere. And it actually became very useful. In fact, I put it above my computer in my research lab because it kept them in the forefront of the experimentation. It's like, okay, this is what you're trying to prevent. Right? You're trying to stop all of these threats. These things are attacking the information that you're presenting, so you need to stop them. Right? So how do you design it? Or how do you design studies to remove as many of those as possible? Right? There's lots of ways to control for threats, right? But adequate design is by far the best. Right? If you design a quality experiment, you will control for as many threats as you possibly can. Okay? There's a quote on Dean Cruz's door that says something up to the effect of, "You can't fix with statistics what you buggered by design." And the point is that no matter how, the point is that if you screw up your design, if you screw up your experiment, statistics aren't going to save the day. You can't fix validity with statistics. Right? So if you've got low internal validity, you can't fix that with a fancy stat. Although a lot of people will try. And there are some things you can do, but in general, it doesn't cover for a piss poor experiment. Right? A piss poor experiment is a piss poor experiment. There's nothing more to it than that. Low internal validity is low internal validity, and you may be able to draw some conclusions based on some fancy statistical techniques and data conversions and things like that. But you're really you're playing with fire at that point. Right? Sometimes you can rule these things out logically. Right? So we may be able to say that there's no way that a maturation effect was present on the data because the data didn't change, right? So a maturation effect would indicate that the data was changing, right? So if the data didn't change, maybe there was another threat to validity, but it definitely wasn't maturation, right? So you can rule things out along those lines. Right? Sometimes if you know, let me back that up, sorry about that. Sometimes if you know that the threat is coming, you can measure it. Right? If you have the potential for a maturation effect happening in your study, maybe you can measure it by using a control group and capture that maturation variable and then use that as a comparator, so to speak. Right? So, and even if you don't plan on it, maybe you have some data somewhere that did allow you to capture that threat to validity. This is a very challenging one, by the way, to know that it's going to happen. Right? First off, you have to predict that it's going to happen. And normally, if you can predict that a threat to validity was going to happen, you would have tried to control for it in your experiment. So you're going to predict that it's going to happen, but you couldn't control for it in your experiment, so you're going to kind of just welcome it in, right? And then try to measure it, to capture it. And then you can see if you can rule it out, right? Using the information that you gathered by measuring it. Right? So anyway, that's the general procedure for how you control them. The rest of the quarter is literally going to be about how you actually design at least a lot of the quarter is going to be how you design experiments and how they control for these things specifically, and how you actually manually do this in the Lincoln Logs approach to doing experimentation. But in a nutshell, it's just those three things. That's how you deal with this stuff. So let's look into statistical conclusion validity. And let's first look at a good definition of it here. In other words, do the effect and cause covary? That's the question that you're after. Right? So do the effect and the cause covary? If you manipulate the independent variable, does the dependent variable change? That's what we mean by covary. They both change together. Right? We have two types of error that can happen here. Now, normally I have an entire slide set on error, so you might need to do a little bit of additional research on what these errors are, but I'll go over them in brief here. Type 1 is known as a false positive. Type 2 is known as a false negative. Right? So when you're thinking about statistical conclusion validity, this is where type 1 and type 2 error can really start to come to play. For example, based on your statistics, you could conclude that there is a difference, you could conclude that there is an effect, that your independent variable caused something. In other words, you found a causal relation between the IV and the DV. It's possible that your statistic is wrong, right? Or that there was some randomness in there, and there's some certain things that happen with statistics, right? And that you found something that really isn't there. That is a type 1 error. Finding something that is not there. That's a false positive. And that's type 1 error. The other type of error that can happen in a particular study is type 2 error, which is a false negative. In other words, not finding something that is there. It's entirely possible that your statistics are not sensitive enough to detect the effect that is present in your data. Now, why might that happen? Well, there's a lot of reasons why that might happen, and we're going to run into that one here in just a moment. But really it's about probably the most common situation there is low statistical power. So we'll come back to that in a second. Right? So that's type 1 and type 2 error. Those are the types of situations that often arise in statistics, and you need to know if they're happening or if they're not. You need to be able to say with what probability they're happening, and sometimes it's easy, sometimes it's not. Right? The other question that we're asking with statistical conclusion validity is how strong do they do so? In other words, if they do covary, how strongly do they covary? Right? Is it a weak effect? Is it a medium effect? Is it a strong effect? We'll often refer to that as effect size. Right? We can misjudge the strength of that relation based on all sorts of factors, and we'll talk about those factors with you in the textbook and with this particular class. So let's go through a little bit of refresher here if you're forgetting a little bit about statistics. Okay? Remember, we talk about statistical significance. It's a very special thing. All right? It's not, significance in statistics has a very, very specific meaning. It doesn't mean important. It doesn't mean meaningful. It means that we are confident that our inference is not due to random chance. In other words, we set a confidence level. It's arbitrary. All right? We'll talk about that number here in a second. Actually, let me just pull it up. So we'll set that number, okay, the alpha level, as we say. So, and oftentimes you'll see an alpha level set at 0.05. An alpha level at 0.05 literally means that we are confident that our finding happened. Okay, with we're 95% confident that our finding was not due to chance. In other words, we have a 5% BS factor. Okay? The 5% chance that our statistic is misleading us and that this difference is actually really due to chance alone. We'll talk more about that later on, and then we'll go into gross detail about how we actually set significance and assess it. But it's really straightforward, and I'm going to give you a real quick rundown here before we go on any further. When you're looking at statistics, when you're using statistics, you're looking at data. The data that you're looking at, I'm going to set up an experiment that has a control group and an experimental group. Right? So the data that we're looking at can fall into two categories. Right? Or falls into those two categories, the data from the control group, the data from the experimental group. The differences between the numbers, right, between the control group and the experimental group, the differences that are due only to the independent variable, that is what we call, oh shoot, now I'm going to forget the term, between groups differences, right? Which is also termed, what was it? This stuff always happens when I don't have it on my slides. Systematic variance, all right? So to refresh here and restate my blubbering here, the differences between groups, between the numbers, right, that are due to the independent variable is, I can't believe it, I just drew a blank again. See, there are humor in these things every once in a while. It's hilarious. I can see it on the board because I write this every quarter. Anyway, is systematic variance. So the systematic variance is the variance that is due to the independent variable, the differences between the groups. The differences that are inside each group, right? So the differences within each group, those are called unsystematic variance. Right? And when we're doing statistics, what we typically do is we take the systematic variance and divide it by the unsystematic variance, and we get a result. That result we can look up on a particular table. Right? And we look at that, and we'll talk about what those tables are later on. But when we look that up on a table, then we will see what the probability of that number occurring is. Right? So systematic variance divided by unsystematic variance gives us a result. Now there's a lot of ways to get that, but we'll talk about that later on. But that result then gets looked up on a table that's appropriate for the statistic that we're using, and we decide what the probability of that particular number occurring was. Right? And if that probability is less than our alpha level, then we say it is significant. And that's all there is to it. There's really nothing more than that. How we go about getting that number is convoluted, twisted, and there's all sorts of different formulas, and an ANOVA, and a t-test, and all sorts of different regressions, and all these different types of statistical techniques we can use, and they're all different, but they all boil down to that same basic procedure, which is systematic variance divided by unsystematic variance equals inferential statistic. So then we look that statistic up. If it's less than our probability level that we have, our p-value that we have set, p-value is also another way of saying alpha level. So is it less than our alpha level? Then we're good. All right. That alpha level is completely arbitrary. Some people choose 0.05, some people choose 0.01. Physics uses 0.0000002. All right, so there's all sorts of different alpha levels that are out there, but in psychology we typically use 0.05. All right, let's look at some of these threats to statistical conclusion. Low statistical power, probably the most common one that you run into, and it's a bugger. All right, there's lots of ways to fix it, and your book is going to go over those things. But essentially all it says is your design could not have detected the effect, even if there was one. So let's say that the independent variable was actually going to cause some change, or it actually does have some power and was actually going to cause some change, but your design was set up in a way that was never going to detect it. This is specifically a design issue. Almost always this is a design issue, and it can be fixed in all sorts of ways. And the most common way that people fix low power is by getting more subjects, okay, and running a bigger sample size. So if you've got 20 subjects and you have no significant effect, your first question would be, did I have enough power? I might not have had enough power to detect an effect. So then you run it with 200 and you find out, did you have an effect there? If the answer is no, then you probably don't have a variable that's actually changing anything. But you never know. There's all sorts of other criteria that go along with that. And again, there's a bunch of procedures in your book about how to control for low statistical power. The next threat is violating assumptions of the test statistics. Don't do it. That's all there is to it. We'll go over that stuff later. This is my pet peeve. I could spend, 2 or 3 days sitting here talking about this stuff. Each statistic has its own assumption. There's a reason it has an assumption. It's because that's the only way the statistic will do what it's intended to do. Therefore, if you violate your assumption, game over. Your statistic doesn't mean anything. Right? Just like if you make assumptions about friends or family or whatever the heck it may be, and you draw conclusions based on those assumptions, and maybe your assumption was wrong to begin with, and now your conclusions are wrong, and the whole world goes to pot, right? Or it gets all pear-shaped, and it's now a bugger to deal with. Okay? So don't violate your assumptions. Right? A lot of those assumptions are going to be like normally distributed data, homoscedasticity. Let's see, what are some of the other ones that might exist? Homogeneity of variance, independence. There's all sorts of different assumptions that exist for each statistic, and you need to make sure you meet those assumptions. Okay? And again, hopefully as a consumer of information, as you're reading these statistics, you'll be like, I wonder if they met their assumptions. And a good author, a good researcher will tell you if they met their assumptions. The problem is that a lot of times in the field they don't tell you. Okay? In other words, use the correct statistic. If you don't meet your assumptions, don't continue on with the same stat. Use the one that you're supposed to use. And I'm going to teach you guys that. Fishing. While it may be fun on a river, it's not a good idea in data analysis. All right? Here's why. Let's take that p-value. Okay. Remember, we set it at 0.05. That means that we're 95% confident, right? In a sense. So what we're going to do is we're going to take those probabilities and multiply them by each other. So we got a 95% probability of not making an error, 95% probability of not making an error, 95% probability of not making an error. You see what we're doing here. So each time we do a test, each time we do an experiment or a study on a particular data set, we have a 95% chance of not making an error, right? So if we do 3 tests, we're going to multiply that 95% by itself, right? So now we're going to end up with 0.857. Well, it doesn't seem too bad. We've got an 85% chance of not making an error here. Now let's flip that around and see what the chances of making a type 1 error are. So we do 1 minus 0.857 equals a 14.3% chance that you buggered up. Okay? Remember, you set this number arbitrarily, right? So if you choose 0.05, this is the number that you end up with. So when you start fishing for data and doing stuff when you start just doing testing and testing and testing and testing and testing, you're multiplying this hidden probability. You don't see the probability. You don't see it. It doesn't sit there and stare you in the face. It's something that's going on every time you run a test. It's not calculated in the test. The tests are all set at 0.05, but it's a real problem because as you're doing the experimentation, this is building up, and it's not recorded anywhere. It's like, ooh, I'm going to test this. Ooh, I'm going to test this. Ooh, I wonder if there's a difference here. And you just kind of get into it. And as a researcher, I know it's really easy just to get into it and start pulling all these numbers. And then all of a sudden you realize, I just ran 6 tests on my data. And I have a real big chance of making a type 1 error now, finding something that's not really there. And oops, I didn't do anything to correct for it. So you can correct it. There's a really easy correction. And it's just taking your p-value and dividing it by the number of tests you have. That's all there is to it. So if you take your p-value of 0.05 and you're making 5 tests, divide the 0.05 by 5, you can do the math from there, and now you have a much lower p-value, right? So you have to be more strict in your statistical interpretation. So that's the easy way to deal with phishing, right? Is adjusting your p-values by the number of tests you're doing. But really, you shouldn't do phishing. It's just not a good idea. You should take your tests ahead of time. You plan your tests ahead of time and then leave it at that. It's called a priori testing. You do what you're supposed to do. All right, let's keep going. More unreliability of measures. That's pretty straightforward. If the measures aren't reliable, then you're not going to be able to draw any conclusions from them. Imagine an intelligence test that gives you a score of 100 today, and tomorrow it gives you a score of 120, and the day after it gives you a score of 105. Or 73 or 69. So if you start to think about your jobs and you're going to think that magic number 70 with intelligence tests, right? Well, guess what? If it's not a reliable measure, it might be 70 today, 80 tomorrow, 60 the day after, and so on and so forth. That's not good. Right? Now you can't really draw any conclusions statistically speaking. Right? Restriction of range. This is another one. Ceiling effects and floor effects. This is where, like for example, I've done blackboard testing where I've given students the opportunity to take the test as many times as they want. Well, that's going to produce a ceiling effect. Everybody's going to score very highly by the end of the quarter, right? Because they're going to take those tests as many times as they can. A floor effect is the opposite. The data is driven down. It's not allowed to go above a certain range. So if you have ceiling effects and floor effects, then when you run your statistics, you won't be able to detect any effects because everybody maximized or minimized, whatever it may be. Unreliability of treatment implementation. All right? Was the treatment done correctly? Okay. Was there fidelity across groups? In other words, let's say you've got 50 people in your IV in your independent variable condition and 50 people in your control condition. So the question is, did you treat all 50 people exactly the same with that treatment? Did you do the same thing? This is why we standardize procedures and standardize the instructions on tests and things like that. That way we're making sure that everybody gets treated the same. It's called treatment fidelity. Right? Was the treatment implemented the way it was supposed to be implemented? Extraneous variance in the experimental setting. A fancy way of saying the environment is messing with you. Simple examples here. Was the heat the same in the rooms that you're doing the experiments in? So was the control group in a room that had a 40-degree temperature and the experimental group was in a room that had a 110-degree temperature? That's a dramatic difference, and that's the extraneous variance that we're talking about here. And it can be anything. It can be noise, it can be heat, it can be sights and sounds and whatever. It can be all sorts of stuff. Okay? So in other words, standardized. All right, more threats. Heterogeneity of subjects. Okay? In other words, are your two groups functionally equal? Are they the way they're supposed to be, right? So your groups are supposed to be equal, and that's supposed to be dealt with through random assignment, right? But sometimes it ends up not being the case. Maybe you have a bunch more males in one group than in the other group. Maybe you've got socioeconomic statuses that are distributed differently, things like that. In other words, it might be that those differences are driving differences or failing to drive differences between your groups, and that your statistics aren't detecting an effect, and that's because of this issue here. Inaccurate effect size measures. Right? There's all sorts of effect size measures of effect size, coincidence, correlation, so on and so forth. There's a bunch of those different things. The question is, did you use a stat that is appropriate to the data? Now, that one has kind of shown up a couple of times, but the idea is, was the stat properly chosen? If it wasn't, then you might not be able to assess any differences here. That's pretty much it for statistical conclusion validity threats. So if you want to take a little break, now's a good time. All right, break's over. Threats to internal validity. Ambiguous temporal precedence. I love that one. It sounds just cool, right? Ambiguous temporal precedence. Go back to John Stuart Mill. Right? Go back to him and remember what he said. He said that the cause has to precede the effect. Sometimes, though, you get these odd circular patterns where the cause causes the effect causes the cause. That's kind of weird, right? And the effect influences the cause, I should say. So in other words, let's say I give you a stereotype. Okay? And this is just a BS stereotype. It is not true, so do not ever perpetuate what I'm about to tell you. Right? Women are bad at science and math. Okay? If girls are in the school are told that they're bad at science and math, that could be your independent variable. Now you give them a test on mathematics, and then they do bad on the test. Now the test is going to influence the independent variable. Right? The result, and they say, okay, I did bad on the test, so now I'm going back and it's influencing the independent variable because it's confirming what I already have and blah, 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 and all this stuff, and it's a mess. Right? So you need to make sure you have independence of measurements. You need to make sure that you have the cause, the independent variable really does come before the dependent variable, and that dependent variable can't in turn affect the independent variable at all. And selection bias is really straightforward. Did you select people in the proper way? Did you randomly select them? Did you randomly assign them? If you didn't, then you're not going to be able to. You're not necessarily going to be able to draw certain conclusions from your data. Right? Who did you select to be in the study? Just remember this. Okay? 4 out of 5 dentists choose Crest. And on the next commercial on the next channel, 4 out of 5 dentists choose Colgate. Okay? So your question should be which dentists? In other words, you have an issue with internal validity on the selection issue. Right? You don't have a representative sample, or you don't have the appropriate sample. History effects. This is when something happens that can explain, something happens to one of the groups, either a control group or an experimental group, during the experiment, okay, that is not something you were intending. In other words, they experience something else that could then change the results of the experiment. A cheesy but realistic example is a fire alarm going off. Imagine if you have a fire alarm going off during the middle of your intervention for your experimental group. And then you run your control group through and they did not have the fire alarm. Now you have a difference between your groups that was not planned, and it may, doesn't have to, but it may have caused a difference between your groups, therefore you have a history effect. Maturation, this is when groups naturally change, right? So kids naturally change, they mature. So if you're capturing maturation variables, or if you're capturing natural change, it may be due to maturation, or it may be due to your independent variable. So this starts to become a big problem when you're doing multiple measurements over time. Right? Regression artifacts, you might have heard this before as regression toward the mean. Right? Regression artifacts is preferred because it doesn't have to go toward the mean. It can go all sorts of directions. The idea is that on any given measurement, it's not going to be perfectly accurate. So we talk about observed score versus true score. You may have heard that. Well, the idea and regression artifacts play into that. That the more we test you, the more we are likely going to be able to assess your true score. Right? The closer we're going to get to that. But each measurement by itself might be off. So if you have 2 measurements, one day you may just having an off day or whatever, and you take a physics test or something and your score is really, really low. But in reality, you know more than that. You were just really, really tired. So when you come back and do your post-test, you're well rested and you do it again and it looks like a dramatic improvement. That's a regression artifact. It had nothing to do with whatever the independent variable was. It had simply to do with this natural change. Attrition, mortality, people leaving your study, dozens of reasons why. You can imagine why. All right? But this is a major issue. Testing effects. Right? Just giving you the test may influence you the second time that you take the test. So pre-test, post-test stuff, it's possible that the pre-test affects your post-test score just because you've been exposed to the test. Okay? Instrumentation, the instrument itself may change. Right? It may not be as good of an instrument as what it used to be. Right? Trying to think of a good example here. The instrument the example I want to give is kind of cheesy, but oh, what the hell. All right. There's a chunk of platinum in France. I know, told you it was cheesy. No, seriously, there's a chunk of platinum in France that they use to set the standard weight of a kilogram. So there's literally this chunk of platinum, and it's exactly 1 kilogram, and that's what they use to establish how much a kilogram really weighs. Okay? The problem is that over the years, the platinum has started to degrade. And that's normal. Platinum is a very stable metal, but it still degrades over time, very, very, very slowly. So today, okay, the chunk of platinum that's sitting in that vault is actually lighter than what it was when it was first put in there. And we're talking by an unbelievably minuscule amount, but if you were weighing, say, the Earth in kilograms, it would make a difference between then and now. Right? So that's an example of instrumentation change. Right? So how much a kilogram is, according to this one chunk of platinum, has actually changed. Right? Let's see, another way to think of instrumentation. Maybe your instrument is not calibrated very well. You guys have all seen this on the bathroom scale. Holy cow, I weigh 233 pounds. Yeah, no, I don't. I adjust that thing and put that 0 back to normal. Okay, I just weigh 195. Right? That type of thing. These things combine with each other. You can have history selection effects, maturation testing effects, regression and attrition effects, and so on and so forth. And they kind of become an infinite sort of threat in and to themselves. Random assignment takes care of a majority of these, right? Believe it or not. These are most easily addressed through random assignment. Right? And that's why quote-unquote true experiments require random assignment, is because it rules out all these threats to internal validity. Does it guarantee that it didn't happen? No, but it makes it really extremely unlikely. All right, construct validity. So as I hinted at before, what is the standard measure of human development? It's not like height. Height is easy, measured in inches, millimeters, centimeters, whatever, right? But the standard measure of human development, is it some scale? Is it some Piagetian assessment? Is it some, who knows what it is, right? It's not standard. So the question is, are we really measuring it, right? So the construct of development needs a measure. Okay? The question is, does the measure match the construct? First, in order to make this work, we need to decide what makes up a construct. For example, intelligence. What is intelligence? Think about it for a minute. You guys may be experts in this already. You've had classes in it. Think about what intelligence is. Is it just your ability to answer certain types of questions? Okay, cool. Well, you may be intelligence in physics. Yeah, hey, I'm great. I'm plenty intelligent in psychology, but put me into biology and I'm not so great anymore. Right? Put me in history and I'm not so great anymore. Right? So does that mean I'm not intelligent or just intelligent in psychology? Well, what's that construct of intelligence? Does it have to measure general intelligence? Does it have to measure specific intelligence? So you get the idea here, right? So what goes into it? We have to make sure we know what goes into it, right? So that's part of construct validity. Right? When we measure these constructs, what we're really talking about is something called psychometrics, right? The scales, the observations, the inferences you make, those are all types of measurements of constructs, right? So when you observe a kid in the classroom being violent and hitting other kids, you are at least in some way measuring the construct of aggression, right? Because he's punching somebody or hitting somebody. But there's other ways to be aggressive. You could be passive aggressive, and that could be included in the construct of aggression, right? So how are you going to assess that? So construct validity is about how we get at those constructs, right? And as you might expect, there's threats to it. All right. Inadequate explication of constructs. In other words, did we define the construct right? Did we, think of the intelligence thing. If I define intelligence just as my ability to perform on a particular test, say that a whisk or whatever, right? Is that an accurate measure of the construct of intelligence? Because I guarantee you a dolphin's not going to do very well on that whisk, but they're pretty damn smart, right? They're pretty intelligent creatures. So maybe we haven't defined our construct of intelligence well enough to go across species yet, right? It's a challenge. Right? Construct confounding. Okay? Two constructs measured as one. Maybe you're measuring intelligence and empathy at the same time. So maybe your survey is capturing both of those things. That's not good, right? Because then you're not going to have an accurate measure of the construct of intelligence. Mono-operation bias, measuring the construct in only one way. Right? So are you doing it with just a survey form? Or just a direct observation? Or just an interview with somebody else? Right? Because if I give you a survey and have you write your answers on that survey or circle the answers or whatever it may be, I'm assuming that you can read and read well and understand what you're reading. Well, maybe you can't. So now what? I would say that you're not intelligent because you can't read? That's not right. So you have a mono operation bias. Maybe if I ask the questions, I'll come up with a different structure or a different outcome on that intelligence scale. So that's mono operation bias. Mono method bias, recording and interviewing in the same way. Right? So again, this is very similar to mono operation. Mono operation meaning you're just assessing it in one way, basically with one form. Mono method is more like what I was describing about with that particular tool. So is it just a visual measurement? Is it a auditory one? That type of thing. Okay. Confounding constructs with levels of constructs. Think of it this way. Levels of alcohol will produce different effects. If I give you a drop of alcohol, and then I can say, oh, look, alcohol didn't affect your driving behavior at all, right? But if I give you a gallon of alcohol, it will affect your driving behavior. So those are the levels of things that we're thinking about. So maybe our measurement is not good at detecting small amounts of intelligence. Maybe it can detect high levels of intelligence. So we have to worry about that. And then we may conclude that the kid didn't have any intelligence or was low on the intelligence scale, but it was really our scale that was a problem, and it was just measuring a certain level of that construct and not an overall construct. Treatment-sensitive factorial structure. I kind of talked about this earlier. The treatment changes the participant in a way that causes them to react differently to the assessment. Right? So this is a circular sort of thing. Right? It's a type of instrumentation effect where you end up making you more sensitive to the... this is a hard one to describe. Your book's got a good example, but I'm trying not to give the same one. Again, treatment sensitive, it literally when I do something in the treatment that might change the way you think completely as a whole, which then may change your interpretation of the survey instrument and that I'm using to assess you in some way, shape, or form. And as a result, I biased my measurement of that construct. Really straightforward, reactive self-report changes. This is an intervention tool. This is so prevalent that we use it as an intervention tool. That self-report can cause you to change your own behavior. So you can react just because you're now becoming self-aware. Reactivity to the experimental situation. Right? The experimental situation itself can produce feelings in you. It may freak you out. It may make you nervous. Evaluation, apprehension, those types of things. Experimenter expectancies. And the experimenter themselves may have certain expectancies. It's a type of bias that the experimenter brings to it. And I may be hinting at particular answers, or I may be giving things away, or I may be setting up the scenario to where I'm going to influence your results somehow in some way, shape, or form. Usually the experimenter doesn't even know they're doing this, but it happens. Novelty and disruption effects, right? Compensatory, novelty and disruption, sorry, I'm just jumping on. Novelty and disruption, the fact that you're participating in this study, right? The fact that it's new and that you're becoming a part of it is something that's kind of cool, right? And maybe that in itself affects your behavior. Or maybe having you participate in the study disrupts your daily life to a level that you don't score normally on whatever construct or on whatever assessment it is I'm doing, which may cause me to draw conclusions about whatever that construct is, which are inaccurate. It was just based on a disruption. Compensatory equalization. Right? This is where one group compensates for being in that group and they try harder, right? Or they try worse, right? So they got both of them here, equalization and rivalry, where they try to compete with each other. One group's going to work to be better than the other group, or equalization, one group's going to try and catch up to the other group. Usually it's the control group that's doing the catching up, and so on and so forth. But this is where the people know what condition they're in, and they change their behavior accordingly. Another one is resentful demoralization, right? You're resentful that you're participating in this that you're part of this one group, right? And it demoralizes you and causes you to change your scores. Right? Treatment diffusion, this is where the two groups talk to each other. right? And that the effect of the independent variable bleeds over to the control group simply because they're talking about what's going on, right? Or somehow experiencing that independent variable even though they shouldn't be. All right, last type of validity to go over, external, right? So in other words, do the results of your study generalize beyond your study? Does the study sample, can you generalize from your study sample out to the population? Can you generalize from your study sample to a smaller group or an individual? That's actually, in my opinion, that's harder, right? Our science isn't, the majority of psychology is not set up to predict the behavior of an individual. It's to predict the behavior of society. It's to predict the behavior of people in general. The average person, we can predict that really well, but we can't predict what one person will do. I can't predict what you'll do. I can't predict how you'll react or what the person on your left will how they'll react. Right? So it's so external validity isn't just about going from the sample up to the population. It's also about generalizing to individuals. Will it generalize to a similar sample? Okay, so if I get the same types of people from the same school district and run the study again, will the results be the same? Or what happens if I get a different sample, maybe from a different country that's still westernized or something, but hey, maybe I get a group of people from Germany and we try this again, or from Australia and we try it again, will it be the same? Okay. So a bunch of stuff that affects that as well. Interaction of the causal relationship with units. Okay. In other words, was the sample too specific? Did the units being the subjects, right? Your authors choose units. I don't know why. Participants, subjects, units, all the same, right? So interaction with the causal relationship with units. Did it only work with those particular people? Was it too specific? Right? Did you have too narrow of a sample? Right? Interaction of the causal relationship over treatment variations. Right? Slight variations in the independent variable may result in different inferences. Right? If I tweak direct instruction just a little bit, right? If I am even off for 5 minutes during a DI session, it may completely change the results. Right? So that's an interaction, and it may not generalize accordingly. Right? Interaction of the causal relationship with outcomes. Did you measure enough things? Maybe your causal relationship, maybe you didn't detect it simply because you didn't measure enough things. Maybe it's going to affect more things than just, maybe your IV will affect more than just one particular behavior. How about with settings? Right? Are your findings just because of that one particular setting? Was it just successful because you did the experiment in a laboratory and not in the classroom? Context-dependent mediation. Is there a mediating variable? Okay, that only mediates in a given context. Right? In other words, I'm trying to think of my example I had for this, but think about social skills. Social skills may be really useful in some contexts, but maybe not so useful in other contexts. So it may be a mediating variable for something, but those social skills are only going to be valuable in one particular setting, right? So, and that's usually in a setting where you're being social, right? So they mediate the effect of an independent variable, but they do it only in one context and not in another. All right, how do we address some of this external validity stuff? Well, right off the bat, random sampling and purposive sampling is going to be the ways we deal with this, right? So if you can do it, if you can do real, true random sampling, like stratified random sampling or simple random sampling, you should, but it's not that common. Your book talked about that. We talked about that in the last lecture. It's rare to be able to truly randomly sample from within a population of fourth graders. Okay? Maybe you can randomly sample from within a population of fourth graders at a particular school, but that's getting away from a real random sample of fourth graders as a whole. It's becoming a purposive sample. Right? In other words, we need to know the limitations of our sampling method. Like I said, if we're going to do this purposive sample, we have to know that it might not generalize to other people. We have to know that it's only going to be valid for fourth graders at this school. Then we're going to try this intervention again at another school or another school district in another state. And if we get those same results, now we're building that external validity through reliability. We're replicating the experiment, we're establishing some reliability for the independent variable, and as a result, we're building external validity even using a purposive sample. Right? So you can do it that way. Right? So, but you have to know the limitations of your sampling method to know that you should do this. Right? Know who the findings apply to, and when evaluating, be critical. Right? So when you're evaluating other studies out there, you should be really critical, but also understand that there's almost no way to get a true random sample of fourth graders. It's functionally impossible. We can describe how to do it. Randomly sample from all fourth graders in the country. Done. Yes. That's a bunch of hogwash. How are you going to pull it off? Right? So when you're evaluating these studies, just be ready just be ready for that. And understand that the science is about replication and that we're going to try and establish external validity through doing multiple studies, not just one. All right, that's enough on validity. I'll talk to you again soon, probably about some statistics. Cheers.